Computers transfer data in bits, physical systems with two possible states shown by a 0 or a 1. This can be seen on a CD with lands and bits.
With 2 bits, we can represent 4 possible values. With 3 bits, 8 values. And with n bits, 2 to the n possible values.
Quantum computers transfer data using qubits, except rather than holding a distinct value, their quantities could also lie in a superposition between 0 and 1, and we use entanglement for qubits to work together. But what do these terms mean? Whilst a classical bit's value is either a 0 or a 1, in the quantum world, nothing is definite until we measure it. So for a qubit with 2 basis states, represented by ket 0 and ket 1, until it is measured, it is in both of those states at the same time. It's a bit like a spinning coin. Until the coin has been stopped, we could see it as being on both sides at once. And upon measuring the qubit, the probability of which basis state it collapses to is determined by the way the states are combined in the superposition. A superposition closer to resembling a 0 has a higher probability of collapsing to a 0.
To help us talk about entanglement, we're going to talk about pair production.
This is a quantum process where the energy of a photon is converted into mass, in the form of a matter-antimatter pair. The two particles produced each have an intrinsic angular momentum, something we ascribe to a property called spin. Since spin is conserved, spins of the resulting particles must sum to the initial spin of the photon. So when we measure the spin of just one particle, we immediately know the value that the spin of the other particle will collapse to. We can artificially entangle qubits to get them to work together.
This link between the two qubits always remains, no matter the distance between them.
Using operations within a quantum computer, we can affect the superposition of qubits to carry out complex algorithms. But why is this superior to regular bits? We need 8 bits to represent 4 2-bit numbers. However, we can represent those 4 numbers at the same time with only 2 qubits, since their value lies in a superposition between all of the numbers. With 300 qubits, you have the equivalent of 2 to the 300 regular bits, which is as many particles as there are in the universe. Entanglement is then what allows our algorithms to be faster than regular computers.
One type of qubit works by measuring spin of electrons. At extremely low temperatures, an electron spin value doesn't have enough kinetic energy to naturally fluctuate, therefore allowing us to change the superposed value of spin, and hence the qubit, using microwaves. Other qubits use photons instead.
We're here at the Science Museum with a photonic microchip. This quantum processor was once used at the University of Bristol, and it uses photonic qubits which rely on superpositions involving polarization of photons or their presence at all. Quantum computers aren't here to replace classical computers. They won't perform tasks faster if the task just uses a classical algorithm. They're only revolutionary when all states can be used, since with qubits, different operations can be processed at the same time. Therefore, problems such as prime factorization and cryptography can be completed at a much faster pace. Google says their quantum computer is 100 million times faster than their classical counterparts.
So, whilst qubits might be uncertain, their potential in science certainly isn't.